And now we will hear from the Artemis curation lead, Julie Mitchell, on some volatile experiments that she and her team have been working on. Julie, over to you.
Thanks. Just check in. Can you see and hear me?
I can hear you. I can't see you yet, but oh, there you are. Yep.
Okay. Cool. Thanks. Okay, my name is Julie Mitchell. I'm the Artemis curation lead. You may have heard me speaking a little bit earlier today about some of our testing and evaluations that we're doing at the Johnson Space Center to prepare for the return of volatile-rich samples. So this is just, I wouldn't call it a deep dive, but this is a little bit more information than what we got to talk about this morning about what we're doing to help overcome this new challenge that we have. Next slide, please. So everyone knows this already, so I won't spend too much on this, but volatile-rich samples are incredibly important, of course, and we expect to collect them from PSRs, and not only for science purposes, but also as a potential resource for human explorers. So some of the volatiles that could be present in samples are obviously water is a big one, but also other compounds like carbon dioxide, hydrogen sulfide, ammonia, and others. For those of you who are familiar with the L-Cross impact. L-Cross detected all of those compounds and more. And when you look at studies of comets and asteroids, and other volatile compounds in the solar system, there's a whole smorgasbord of volatiles that could be present in PSRs that we haven't encountered yet. So it's potentially very complicated chemistry, along with the fact that everything is also in the presence of some very unique geology in rocks. So we want to collect this stuff, we want to study it, and we know that keeping samples cold are going to at least slow down, if not prevent, chemical reactions and phase changes of these very sensitive volatiles. That said, Artemis 3 is not going to have a flight freezer, and so those samples are going to be returned at room temperature, but they are going to be returned in sealed containers. For future missions like Artemis 5 and beyond, we are planning to have a freezer. It's not definite yet, but we are looking into the benefits of having a flight freezer for that Artemis 5 and beyond mission timeframe. And so the big question that we're trying to answer with our studies at JSC is what will happen to the volatiles in transit from the moon to Earth, and how much will flying a freezer help them? Next slide, please. So we are conducting some sample storage testing at the Johnson Space Center. We have a laboratory called the Planetary Exploration and Astromaterials Research Laboratory, or the PEARL, and we have a whole suite of freezers and analytical instruments that are set up to specifically answer this question and other volatile specific questions. So we are going to be characterizing sample alteration from a lunar volatile-rich simulant at a range of temperatures. So we're going to be looking at room temperature, which mimics the in-flight non-freezer storage conditions, for example, for Artemis 3. We're going to look at minus 20 degrees C because this is the temperature that some of the Apollo cold curated samples were stored at. We're going to look at minus 85 degrees C because that's our initial estimate of what an initial flight freezer would look like. It's also the triple point of hydrogen sulfide. So that way we could at least keep hydrogen sulfide minimized in the gas phase under that temperature. And then finally, we have a liquid nitrogen freezer, which is 77 Kelvin or minus 196 degrees C. And that's representative of the temperature of a lunar PSR. Now, there are PSRs that are colder than that, but in terms of what we expect, at least for the earlier missions, we probably expect people to go to places that are that temperature or warmer. Next slide, please. So in order to facilitate this testing, we have put a lot of work into developing a volatile-rich simulant. And so we started out with a regolith that is a Highlands type regolith. This is a existing regolith that the community is using and has used for some time, the USGS Lunar Highlands type simulant. We have the 4M grain size, and many thanks to John Gruner and colleagues for providing that to us to use for our testing. To that regolith, we add our own volatiles such as water, methanol. We aren't certified to work with ammonia yet, so we're using methylamine, which is chemically similar. We are using small quantities of hydrogen sulfide. carbon dioxide, and for some of our evaluations, we're also looking at formaldehyde. Even though it wasn't detected by LCROSS, it could be present and it would have a significant impact on the chemistry. So we're looking at that as well. So you can see in the photo here, we've made quite a few of these simulants. We have a very robust process for making this, and it is repeatable. And so we are hoping to publish that and release that to the community so other folks can replicate the technique we're using here. And as our lab capabilities expand, we're going to continue to add to the compounds that are listed here. Next slide, please. So our initial testing, we have conducted storage testing of a regolith only and a regolith with water simulant. We have 5 different recipes total that have a increasing complexity as you go from regolith by itself all the way up to the full suite of all the different compounds. We are measuring any gas phase reactions that occur, looking at any reaction products, looking at what happens to the regolith. Is there any surface alteration on the regolith grains? And what we're doing in these tests is we're storing the samples at those different temperatures for 2 weeks. So we are pulling aliquots at different times during that 2 weeks and looking at how the chemistry changes. We have a universal gas analyzer that we're using for quick turnaround analyses, and we have a GCMS that we're using for more detailed, higher precision analyses. You can see in the picture that with some of our practice samples, you can even start to see color changes in the regolith when it's exposed to hydrogen sulfide versus not. So definitely some interesting results forthcoming from that. And so we haven't completed the rest of the testing, but as soon as that's done, we're going to be sharing that with the rest of the community so everybody can make more informed science decisions and operational decisions for Artemis. And I'll stop there. Thanks.
Thank you, Julie. Please stick around for the Q&A if you can.